42 marks, easy. Okay, let's look at this paper. This is the CT2 for Year 10. And we're going through the first question. It is a 42 mark paper, 45 minutes in length, which you can get extra time for. Right, fill in these spaces in the table. So we have got helium, neon, argon, krypton and xenon. So let's turn over the periodic table and we can see that krypton is Kr. So the first thing we do is we write the symbol in the table Kr. Now if I was thinking I'd do the third column, but I wasn't. I was going straight on to the next question. So density, look at the pattern. It goes up. They would accept any reasonable answer here, so I just fixed a number that fit inside the pattern. They would have given you anything that fit between those two numbers, so 1.45 to 2.99. You don't have to know it off by heart. It's a common sense question. What do you think the pattern is? We'll come back to that reactivity in a minute. Some light bulbs contain a metal filament. These light bulbs are filled with argon. Why is argon instead of air used inside the light bulbs? Well, what do we know about argon? It's an unreactive gas. It's got a full outer shell of electrons, so we would write argon is inert or unreactive. You could add it's got a full outer shell of electrons, and I'll do that in a second for extra bonus points. And you would say, therefore, it doesn't react with the hot metal filament inside. The metal filament is what shortens the life. It sort of burns out. So by adding argon, you don't get a reaction with the metal, and we know that all of the noble gases are unreactive. All of the questions are going to be because the gas is unreactive, so we put that in. Now, we know it's unreactive, so we got a pattern of no reaction in that table. So what we'll do is we'll add the last bit to the table. No reaction, no reaction, no reaction, no reaction. Guess what? Xenon? No reaction. So we'll just complete that question, and we can get 5 easy marks for question number 1. It's an unreactive gas. It's a noble gas. It's always the same pattern. I've taught you this. Sodium reacts with water to form sodium hydroxide solution and hydrogen. Complete the balancing of the equation for this reaction. Add the state symbols for each substance. So sodium, then we've got water, which is H2O, sodium hydroxide on the right, and H2. So you don't even have to know the symbols for that reaction. It's given to you. We'll count those all up. So let's put those in. I'll notice I've got 2 H2O in a minute. So if I put the sodiums first, double the sodium, that gives me 2. Double sodium hydroxide to make the sodiums balance. That will also give me 2 oxygens, and the H2 plus the 2 in the NaOH gives me the 4 hydrogens. The H2O is already 2 H2O. They've already balanced that bit for me. And by having 2 H2Os, the whole thing balances for me. Do you see that? Sodium is a solid metal. Water is a liquid. Hydrogen we know is a gas. And the sodium dissolves in water, so it's AQ. You get 1 for balancing the left-hand side, you get 1 mark for balancing the right-hand side, and you get 1 mark for the state symbols. So there's 3 marks straight away. It says, in an experiment, equal-sized pieces of lithium, sodium and potassium are added to separate samples of water. A flame is produced only with potassium because potassium is the most reactive, because it's the one that produces the flame. So in terms of electronic configuration, the increase of reactivity from lithium to sodium potassium, you've got to explain it. Well, we all know it's got 1 in the outer shell, so it can't be the outer shell electron as such, but there's something about that outer shell electron that we've got to explain. So let's go to our periodic table. We've got lithium, sodium, and potassium. Well, hydrogen, helium is period 1, lithium is period 2, so it's got 2 outer shells. Sodium is in period 3, so it's got 3 outer shells, and potassium is in period 4, so it must have 4 outer shells. Let's just do a diagram of that. Now we know it wants to lose those outer shell electrons to get a full outer shell because it's a metal. All metals lose their electrons. And the outer shell to get a complete outer shell by having the next inner shell. To lose the electron is easier when it's further away from the nucleus. The nucleus has got the positive protons. So we can make a comment about that, couldn't we? There's more shells as you go down the periods. So as we go down the group, we get more shells. More shells means there's more shielding, there's a greater distance from the nucleus, and therefore the electrons are lost more easily and the reaction occurs more vigorously. So you've got to link the idea of having a greater distance of the nucleus from the outer shell. So I write the atoms become larger, The electrons, or outer shell electrons, are further from the nucleus. Or I could also say there's more shielding. If you learn about shielding, you could put that in. And then finally, so electrons are more easily lost. It's a really easy 2-mark question because there's 3 things you could say to get those 2 marks. Any of those 2 would have worked. Next question. A teacher demonstrates this experiment. The results are shown in figure 8. So we've got position of metal in water, movement of metal, and effervescence, which is known as bubbling. And you'll notice that there's a pattern there. So it says, I'd like you to describe the experiment, the safety, and how those results would give you the order of reactivity. Well, hopefully you've seen this reaction and you can remember it. If you're really unlucky, it set a fire alarm off because of the smoke. But anyway, so you get a trough or a bowl of water, the same volume each time to make it a fair test. And then you've got to take the metal, and remember they're stored under oil. And that's something we could talk about. You're going to take them out with tongs, wear gloves, safety specs, stand well back, maybe put a safety screen, get the children standing out of the way, or the students standing out of the way. And you've got to get the oil off of it. So you blot the oil off of it with a bit of tissue paper. You cut a small piece, because it can be quite a vigorous reaction. So you don't put the whole thing in, it'll make a big mess. It could be quite dangerous. So you cut a small piece off, then using the tongs, add the metal to the water. And that's a safe thing, is wearing the appropriate personal protective equipment, isn't it? So that's what you're going to write about. Think about what happened and how you would do it. There's plenty of these videos to revise from on YouTube about the alkali metals in water, so you could use your notes, but you could also look up videos here. So how would these results give me the reactivity? Well, let's talk about that. Let's look at the reaction. It talks about the movement. How does it bubble? How vigorous is it? Let's talk about that and how it reacts to reactivity. We know as there's more bubbles, there's more reaction, then the one that fizzes the most must be the most reactive. That makes sense. The one that moves around the fastest on the top of the water, well, that's going to have an indication of how reactive it is. Faster movement is most reactive. And the reactivity, therefore, follows that it goes lithium, which moves around the least and bubbles the least. Sodium is in the middle, and potassium is the most reactive. And you need to make that comment. You could say potassium's most reactive, then sodium, then lithium, because it bubbles the least, or link the ideas. So make it safe, and then look at how the evidence explains it. So you get the section for safety, and then you get the section for the procedure, how you actually do it. And that links to a conclusion. So this is what I would do, this is how I make it safe, and you can do it in any order to get those 6 marks. But these questions are levelled 1, 2 and 3. 1, they don't really know what they're talking about. To 3, they really get it. So this question's about the halogens. So group 7. Describe what you would see with a damp blue litmus paper placed in chlorine gas. It turns damp red litmus paper blue, then bleaches it white. I showed you it. There's lots of videos of it on YouTube. You could revise these, but it's just memory. There's nothing that you need to work out here. It's a memory. So don't say it goes clear, or it's paper. It doesn't go clear. It goes white. It gets bleached because chlorine bleaches things. This is another pattern recognition. These questions always have a pattern recognition when it talks about the groups. Minus 220, minus 101, minus 7. Any reasonable number that fits the pattern. Any reasonable number. Now, I happen to know the actual melting point of iodine. So, but anything that fits the pattern between 20 and 301, you had a huge range. It has to be less than astatine, but it has to be more than bromine. So I just picked a number. I happen to know it's 114. But anything in between. What's the halogen that reacts most vigorously? Well, remember, we've got a pattern, haven't we? It gets more reactive as you go up the group, whereas the group 1 metals go the other way. So we've got a choice of chlorine and fluorine. Doesn't matter which one you pick. Which one would react more vigorously than bromine, chlorine, or you could put fluorine. Doesn't matter. It's just got to be more reactive than bromine. So you go higher up. The examiner wants to see if you can spot the pattern and know the patterns off by heart. 4 easy marks. So a lot of it's memory so far. What's seen when chlorine is added to potassium bromide solutions? So this is about the reactivity and a displacement reaction. So the chlorine is more reactive than the bromine, so the chlorine will displace the bromine, and so you'll see that bromine in the liquid. And bromine, as you know, is like an orange, red, brown colour. So it's potassium bromide, so dissolved in, it's a salt dissolved in water, and it would go orange and brown. It doesn't matter, orange, brown, whatever colour change that you saw when you did it, it's an orange colour anyway. So that's what you would see. Chlorine reacts with potassium bromide to form potassium chloride and bromine. This is an oil rig question. Oxidation is loss of electrons and reduction is gain of electrons. Hopefully you remember that. Let's look. Chlorine. All elements have no electrons gained or lost yet because they haven't reacted. But once the chlorine does react, it becomes a chloride, and so it gains an electron. And we know that reduction is gain. And it says, explain using the equation how you know the chlorine has been reduced. Well, once it's reacted, it's formed a chloride ion. So I just wrote a little note to myself, oil rig, to remember to sentence it in the right way. So chlorine is reduced because it's changed from the element chlorine to the chloride ion, gaining an electron. Once it's gained an electron, by definition, it is reduced. So I write that. Chloride ion, or Cl minus. You could write both. So you get 1 mark for saying that it's gained the electron, and you get 1 mark for saying what it's gone from and to. So chemistry is about change, isn't it? Right, the half equation. This can be a tough one. We've got bromine, which we know is Br2, and the bromide ion, which is a Br minus, but we've got to balance that out. Br2 needs 2 bromide ions to form it. So, I have 2 ways round I was thinking of writing this. Both are correct in the exam, but you've got the Br minus ion, and it's going to lose that electron to become Br2. So you could write 2 bromide ions loses 1 electron each, so 2 bromide ions loses 2 electrons, 1 each, to form the bromine. That's a great way of showing it. Alternatively, there are other ways that you could write it, but you get 1 mark for getting the fact that the bromide forms the bromine, and another one for saying that you need 2 bromides and 2 electrons to come off of those bromides to make it all balance out. This is talking about the reactivity in metals now, question 5. So it says, here's a reactivity series. The method used to extract metals, so they're talking about aluminium, and this is a reactivity series question. This is a smelting question. Iron ore contains iron oxide. You heat the oxide with carbon, and it's not using oil rig this time, it's about oxygen. So iron oxide takes the oxygen off, the carbon takes the oxygen off of the iron, and it gives you the iron metal. So that's a reduction reaction because we're taking the oxygen away, and so we say it's lost oxygen, therefore it's reduced. There's only one question answer here that's correct, which is C. It's not oxidized because we don't put oxygen on it, it's definitely C. Aluminium can't be extracted by heating oxide with carbon. Well, in the reactivity series, we know that carbon's just not reactive enough to take the oxygen from the aluminium. It can't displace it, so we're just going to write that. Aluminium is too reactive. It's a highly reactive metal by comparison. So it's a highly reactive metal. Aluminium's highly reactive. So the carbon can't reduce it. The aluminium cannot be reduced by carbon. You cannot take the oxygen because it's just not reactive enough. The carbon can't do it. And we say that. And that gives you the 2 mark. One for observing that aluminium is too reactive. One for saying that carbon's not reactive enough. You could say either. But note that the aluminium is reactive and that it can't take the oxygen and displace it. So it says predict the method that will have to be used. Well, we know that the other method that we use is electrolysis, because we know that electrolysis is how we extract aluminium. We learnt all about that, didn't we? Dissolve it in cryolite and all that. In recent years, research has been investigating alternative methods of extracting metals from soils. Well, the metals are in low concentration in the soils, but the plants concentrate them by absorbing them through the roots, and so you end up with this concentration of the metal in the plant itself. So what you can do is sow a plant that's very, very good. I think if I remember rightly, top of my head, I might be wrong, but the brassicas are pretty good at doing this. But there's certain plants that are good at taking in these copper ions. So grow the plant. The plant will absorb and accumulate these copper ions in high concentrations in their tissue. So then you just chop the plants down, and then the copper is in the plants. You burn them, and you effectively end up with copper ore, don't you? You end up with this copper concentrated in the ash of the plants that you've dried and harvested and dried. So you can just burn them, and then you can smelt them, and you can actually get copper from them. So the plants absorb copper from the soil, making them more concentrated in copper, or you could say copper ions, because that's technically what they are. And then you harvest those plants, and then you can do a chemical reaction to get the copper out of them. So you're using the plants. Once you burn them, you can leave the copper behind. One disadvantage, well, first of all, it takes a long time because they're plants. Plants grow really slowly, don't they? It's also quite expensive because they don't get a lot of copper by comparison to the ore, because the ore's got quite a lot of metal inside, so that could be a disadvantage. Any disadvantage you can think. It's slow, therefore it's expensive, and time is money in business. 7 marks. Zinc can be extracted by heating zinc oxide with carbon. They're doing an analogue, just like the iron. The products are zinc and carbon. So this is, can you produce an equation from a sentence? So you have zinc reacts with sign. Wouldn't work, because it says zinc can be heat extracted. So that's a product. So the zinc goes on the right. We've got zinc oxide reacting with carbon. And the products are zinc metal and carbon dioxide. So you just write that down. Remember, and is the plus sign. To form is the arrow. Reacts with the plus sign on the left-hand side. In the reaction, zinc loses oxygen. We've been through this before. What type of reaction? Well, if it loses oxygen, it's a reduction reaction. If you add oxygen, it's an oxidation reaction. Iron is extracted from iron oxide. In the extraction process, the iron oxide is heated with carbon to form iron oxide and carbon dioxide. If you turn back a page, it will give you a massive clue. But this one is just one that you have to memorize. It is a right pickle to try and teach this one, because it takes ages to balance. You can balance it if you want to. So you can put your line there and count your ions and do all of that. But actually, memorizing it is the best way to do it. So it is 2, 3, 4, 3. 2, 3, 4, 3. If you want to memorize that reaction, it's a higher tier question, I think. Tough one. At the end of the life cycle, many metals are recycled. 2 advantages. Why do you want to recycle? Well, you don't have to dig it up. You don't have to then smelt it. You don't have to transport it back to the factory once it's smelted and purify it and all that business. You're going to save the environment. It's going to save you money because you don't have to extract it. It preserves the oil reserves, so you don't have to dig up, fresh rock. You can use the metal that's already made. It reduces waste because you don't have to throw the old metal away. Doesn't take as much energy because you're just melting the metal that you've already extracted. You preserve the environment. You preserve the habitats of creatures that you have to displace in order to create the mine or the quarry. There's loads, and you only need to pick 2 of them. Pick your 2 favourites that you remember, and there's 8 marks. Not all of them easy, but they are there to get. And that is the end of the questions, and it's so easy to get 100%. So that's it. Put your corrections down. Think of some action points. Give yourself some smart targets. I didn't know this. I didn't know that. Maybe I don't know the iron oxide reaction off by heart, or maybe I need to remind myself of the reactivity series for metals, or you might need to know the patterns of the halogens of the group 1s. But 42 marks, easy.